All right, this third video for 5.1 is about the difference between linear and angular motion and showing how they are mathematically related. So we have another picture of a meter stick here. I'm going to assign an axis that's really close to the left edge, and then I'm going to draw, as best I can, another version of the meter stick after it's rotated. So I think I've practiced this enough times that I can do it quickly. So I'm going to rotate the meter stick counterclockwise. So far, everything in the videos has been positive displacement. And we're going to talk about two locations on this meter stick. One of them is going to be at the left edge of the meter stick, and the other one is going to be at the right edge of the meter stick. And so we'll call the one at the left edge A, and we'll call the one at the right edge B. And so point A moves this far to get to its new location, and point B moves this far to get to its location. Now, it's very helpful to have like a physical object that you can move, and I'm not going to do this to the scale that I have, but I'm going to put my finger down on this location, and I'm going to rotate the whole ruler, and you can see the difference in what happens to the right edge and the left edge. And you can also see it here visually. Now, what I want you to see, and that you probably saw, is that every part of this meter stick moved by the same angle. However, very clearly, point B moved a much greater linear distance than point A. And so that's what this video is all about. So we'll call them points further from the axis. Move a greater linear distance than points closer to the axis. Now, no point moves less distance than the axis itself. It doesn't have a linear displacement at all. But as you go in either direction, the further you get from the axis, the greater a linear distance those points move. So we have two important takeaways. All parts of an object, when rotated, move the same angular distance, or angular displacement. However, based on location, there will be different linear, and linear in a circular motion is called tangential. So we have angular and we have tangential motion. And so if you call it linear, that's fine, but just be aware that you will see the word tangential a lot in rotation, and that is the same thing as the linear motion of an object. So different linear or tangential displacements. Okay, and so we're going to turn this into a mathematical relationship, and it's really easy because we work with radians. As you can see, as I said already, the further away you get from the axis, the greater that tangential distance. And so that means that the linear motion is proportional to the distance from the axis. So the linear displacement is proportional to the angular displacement and also proportional to the distance from the axis. Now, the distance from the axis, because everything's moving in a circle, we're going to use the variable r for that. And so that is distance from axis. And so we'll do a lot more with r throughout the rest of this unit. So everything works the same way. The tangential displacement of a point on a rotating object is equal to the distance from the axis times the angular displacement of the whole object. Now, sometimes you get a different variable. for linear displacement, and you get a lowercase s for arc length. And so it's the same thing. It's still linear distance, but it's just a linear distance over a curve instead of an exact straight line. So the linear displacement is equal to the distance the point is from the axis times the angular displacement. And this displacement is also in meters. It brings up something important about the unit radians. On the right-hand side of this equation, we have r times delta theta. That's going to be something in meters times something in radians. And what ends up happening is the meters just replace the radians, and you get the units of meters. Radians is not an official unit. It doesn't maintain itself under all conditions. If you're looking purely at angular measurements, then it stays there as a placeholder. But as soon as you multiply something by meters, an angle times meters, you get meters. It just replaces the units of radians. Okay. Moving on, the linear velocity of a point in an object is equal to the distance from the axis that point is times the angular velocity. This pattern continues for acceleration, where we have tangential acceleration equals the distance from the axis times the angular acceleration of the object. This one's just special because it gets a subscript of t for tangential to set it apart from the other type of acceleration that also has to exist for a rotating object, the centripetal. Now, I will derive centripetal acceleration in class. It's a very minor part of this unit. It's really focused on circular motion instead of big objects that are rotating. But basically, if an object is being rotated and it's changing its angular speed, then it has a tangential acceleration in the direction of the circular motion. But it also has a centripetal acceleration in the direction of the center of the circle. So if you were to swing a tennis racket for serving over your head, as you are rotating the tennis racket forward, the front of the tennis racket's accelerating toward the ball, but also you are physically pulling the tennis racket down, giving it centripetal acceleration. You're changing the speed in two ways that adds to the power of the tennis shot. Anyway, there's one example, and that's it.